In this section 15.5, we're going to be computing triple integrals using cylindrical and spherical coordinates. So similar to two-dimensional space when we went from Cartesian or XY to polar, now we're going to go from an XYZ or rectangular coordinates to cylindrical and spherical. So the first thing we're going to look at is we're going to look at our cylindrical coordinates. Cylindrical coordinates are similar to that of polar coordinates. You're going to have an r, you're going to have a theta, but since it's in three-dimensional space, you're going to have this z value as well. The r values we're looking at are not going to be negative. Theta is going to go from 0 to 2 pi. And z can be any real number. The idea is that for any point that you have, you can write that point in three-dimensional space using those three coordinates, r, theta, and z. So our theta is the usual angle measurement in the xy plane, so you're going to go out a theta. And then r is the usual distance out from the origin. And then we have this z value, which would be like a height. And that would get us to our point. Now here are some common shapes that we have in cylindrical coordinates. The first shape that you see is a cylinder. So it's like our usual cylinder. And the way that we describe a cylinder using our cylindrical coordinates is a very simple equation, which is simply r equal to a, where a is that distance out. Theta can be any value, so it's going to go all the way around. And then z can be any value, so we go up and we go down. Very simple formula. We can also, if we restrict our z values, we can create a cylinder that does end. So let's say that our z values are going to go between 0 and 2. Let's say this is 2 here. Then we can just create our usual cylinder that actually does have an ending value. We also have what's called a cylindrical shell. And that would be like those annulus regions where we have an inner circle and an outer circle. So we have in the XY plane, we have this annulus, and then it's going to go up and down some z values. So that would be our cylindrical shell. We can also describe what we call a vertical half plane using cylindrical coordinates. All we have to do is, and it's a very simple equation, it's just theta equal to some value. All we have to do is go out some theta value in the xy plane, and here we're just looking at a half plane. Notice that my z values can be anything, so we go up, we go down. And r can be anything, so our r value is coming out this way, and that will give us our vertical half plane. Another shape that we may see in cylindrical coordinates is this horizontal plane. The equation for a horizontal plane is just a z value. So you just go up to some z value, and remember our thetas are all the way around in this case, and our r values are all the way out. And this would give us a horizontal plane. The last one we're going to look at is our cone. And in this case, the equation of a cone is just a z value equal to some a times r. And that will give us our cone. In the case that a is positive, it's a cone going up, but we can also have a cone going down. And that would be if a is negative. What we're going to do in example 1 is we're going to identify and sketch the following set. So the set we have here is our theta z, where r goes between 1 and 2, theta is 0 to 2 pi, z values are all values greater than or equal to 2. I'm going to go ahead and sketch my coordinate system for x, y, and z. Now r is going out 1 to 2, so maybe I'll go on the x-axis a 1 and a 2. So we go this distance out. Theta is 0 to 2 pi. So remember, theta is just your angle measurement. So we're going to go all the way around for our theta value. So here we have this annulus in the xy plane, but now our z values are greater than or equal to 2. So we're actually going to start at 2. So let me go ahead and erase all this blue stuff. Since we're starting at z equal to 2, I'm going to go up to, oops, oh, that's not going to work. I'm going to go up to 2 for my z value. And then my r values are going to go from 1 to 2. So that would be this annulus. Oh, my sad drawings. And then from there, we're just going to go up with our z values. Okay. Here's my strange shape. It's a cylinder that starts, so it just keeps going up, that starts at a z value of 2. So this would be a cylindrical shell. But it's not the whole shell, right? It's just where our z values are greater than or equal to 2. And again, excuse my sad drawings. Example 2, we have another set where z is equal to 4 minus 2r, and the r values are from 0 to 2. Okay, so let's go ahead and sketch our coordinate system. This is going to be a cone. And I get that from this equation here. Let me rewrite that as z equal to negative 2r. So this negative 2 would be like my a value. So it's like z is equal to a times r, but then it's shifted with this plus 4. So that tells me that it's, instead of having a vertex at the origin here, it's going to be a cone, but I'm going to shift up to 4. And since my a is negative, it's a cone opening downward. So here we have a cone with a vertex at z equal to 4, opening down. So we looked at some shapes. Now what we're going to do is look at the transformation from XYZ to cylindrical. All of the properties that we had before with polar, and this makes sense, right? Because in the XY plane, we're still using r theta. We're still using our polar coordinates. We're just looking at some z value as well. And you can think of z as being like a height. So the relationship between the rectangular coordinates and the cylindrical coordinates are exactly the same as if we were in polar. We're just adding this z value. As before, our r squared is equal to x squared plus y squared. Tangent of theta is y over x. X is equal to r cosine theta. Y is equal to r sine theta. The only difference is z value. What does that transform to? Well, just z. So very simple there. So let's practice going from cylindrical and rectangular. Let's say that we do want to find the cylindrical coordinates and we have rectangular coordinates. So since these are rectangular coordinates, this is an x, a y, and a z. Well, I know that tangent of theta is going to be y over x, so that would be -1. And then tangent is -1 when theta is equal to 3 pi over 4, so that would be in quadrant 2 and quadrant 4, and 7 pi over 4. Remember, our theta values can go from 0 to 2 pi. And I know that r squared is equal to x squared plus y squared. So r squared is equal to 2, which means r is equal to plus or minus 2, but we're only going to use the positive r value. Okay, so the thing is I don't know what theta is. I know what z is. Z is 4. So let's just look at this point. Ignore the z value. Just look at the point for the x and the y value. X is -1 and y is +1. So that means if I'm just looking in the xy plane, again, I don't really care about the z. I'm just trying to figure out what theta value I'm using. I'm in quadrant 2. So my theta value that I'm using has to give me a value in quadrant 2. That tells me that I'm picking theta equal to 3 pi over 4, not 7 pi over 4. So you always have to, if you're in rectangular coordinates, take into consideration what quadrant you're in. So then my coordinates are going to be r first, so that would be positive square root of 2. Theta is 3 pi over 4, and the z value is simply the z value of 4. Oops, sorry. Okay, so that's the idea of going back and forth between rectangular and cylindrical coordinates. Now we're going to look at our integrals. So our integrals over some region D, and here we can look at this diagram. Let's say that we have this region D, this three-dimensional region, and we want to integrate using cylindrical coordinates. Well, similar to polar, remember in polar coordinates our theta was always our constant limits of integration? Well, it's the same in cylindrical. Theta is always constant limits of integration. Now the r and the z can be functions of other variables, but theta can't. So if you have any region D, you're going to look at this shadow in the xy plane, and that will give you our region R, where to describe it, you're going to go from some small theta value to some larger theta value, and that would give you this angle in between. So there's your constant thetas. Your R value can be a function of theta. So you're always looking at the outer R value minus the inner R value to ensure that that value stays positive. So in our limits of integration, we see here that the outer limits are constant limits with respect to theta would be these outside limits from alpha to beta. And then R can be a function of theta, so that would be our inner, and this is the usual order. So now our z value can be a function of x and y. However, remember that x and y, those values are r cosine theta for your x and r sine theta for your y. So in cylindrical, we can write them in terms of cosine and sine. So typically what we do is we have the inner as z, the next as r, and the last as our theta. But remember, cylindrical is just polar with height. So we also need that r in there. It's like the r d theta, but now we're adding our dz. And if we're going to integrate over some function, then typically we're trying to find mass, right? We're taking a volume as our region, d, and then we're going to a fourth dimension, which is usually mass. So that function would be a density function. Now let's look at example 4. I want to evaluate this triple integral, but I want to use cylindrical coordinates. So this is written in terms of x, y, z. Now remember my z values, and that would be my inner integral. My z values stay the same. I just have to figure out how to write the x's and the y's in terms of r theta. So it's just like going back and going to what we did with polar coordinates. So my z values go from -1 to +1. And my x values go from negative square root of 1 minus y squared to positive square root of 1 minus y squared. My y values, which would be the outer integral, are going from 0 to 1. So we already know what the z value is. It's the x and the y that we need to figure out. So notice that my y values are going from 0 to 1. So I've only got positive y values. Look at the x values. And now it might be helpful if we go ahead and look at maybe one side of this inequality. The x values are less than or equal to the square root of 1 minus y squared. Or in other words, x squared is equal to 1 minus y squared. And I get x squared plus y squared equal to 1. That's the unit circle. However, my y values are going from 0 to 1, which tells me that this is a half circle. It's the unit circle, so the radius r is going to go from 0 to 1. And the theta values will start here at theta is equal to 0, go all the way around, and end at theta is equal to pi. I have my limits of integration. Now I can change this integral into cylindrical coordinates. The outer integral is going to be my theta values from 0 to pi, then r from 0 to 1, and my z values were -1 to 1. What about my integrand? Well, the x squared, y squared, is just r squared. So this becomes r squared to the 5/2. And then I have a dz. However, remember I'm going into polar, so I have an r dr d theta. Well, before we evaluate this integral, why don't I bring all this together? So this is r squared to the 5/2, that would just be r to the 5th. But then I have this other r out there, so that would be r to the 6th. So this is r to the 6th dz dr d theta. All my limits of integration are constant, so I can integrate this in whatever order I want, but I'll just do it in the order that I'm reading it. So if I integrate with respect to z first, remember r is constant, so this is 0 to pi, 0 to 1, z r to the 6 evaluated from -1 to 1 dr d theta. And that would be negative r to the 6 minus positive r to the 6. Sorry, that was backwards. That is r to the 6 minus a negative r to the 6, which turns out to be 2r to the 6. My integral will be 0 to pi, 0 to 1, 2r to the 6 dr d theta. And now I'm integrating with respect to r, so that's going to be r to the 7 over 7. I have integral from 0 to pi, 2r to the 7 over 7, evaluated from 0 to 1 d theta. The integral from 0 to pi, evaluating at 1 just gives me 2/7, and 0, that's gone. So this is just the integral of 2 over 7 d theta. And that will become 2 pi over 7, since this is 2 over 7 theta evaluated from 0 to pi. So 2 pi over 7. Let's do another example. So we want to find the mass of the solid bounded by the paraboloid z equal to 1 minus r squared and the plane z is equal to 0 when the density of the region is this function 3 minus z. So since this is the density function, this is going to be our integrand, which makes sense since we're trying to find a mass. So all we have to do is set up our limits of integration. I'm going to sketch my region. So the region D is bounded by this paraboloid, which is z equal to 1 minus r squared, and the plane z is equal to 0. Well, the plane z is equal to 0 is simply the xy plane. And this paraboloid, well, when r is 0, z is 1. And when z is 0, your r value coming out, imagine it coming out on the x and the y plane, would be 1. So you get this paraboloid opening downward where the base is a circle. And if you're not sure if that's the description of this, then go ahead and replace the r squared with x squared plus y squared and graph it like you normally would. So remember, we're looking at what this shape is in the xy plane. That would happen when z is equal to 0. So this is going to be 1 minus x squared minus y squared, which gives me x squared plus y squared equal to 1. So that region in the xy plane is just simply the unit circle. That also tells me my theta values. It's a complete circle, so my theta values are going to go between 0 and 2 pi. Since it's the unit circle, my r values are going to go from 0 to 1. And what about my z values? Well, I know I'm bounded below by z is equal to 0, and above I'm bounded by 1 minus r squared. So I have my limits of integration. My mass is simply, I'm going to go theta on the outside, 0 to 2 pi. R is 0 to 1. My z values go from 0 to 1 minus r squared, and this is already in cylindrical. And now look at my density function. That's 3 minus z. That's fine too. I don't have to change anything. This is a dz, and then I have my r, dr, d theta. And that's what I'm going to integrate. So it looks like my integral on the inside is just 3z minus z squared over 2. So 0 to 2 pi, 0 to 1, 3z minus z squared over 2. This might be a little bit icky because I'm replacing z squared with 1 minus r squared. 0 to 2 pi, 0 to 1. This is going to be 3 times, I'll keep it in a bracket, 1 minus r squared minus 1 minus r squared squared over 2. And then when I put in 0 for z, that goes away. And we have an r dr d theta. If I go ahead and simplify inside the brackets, I end up, I think I'll just multiply everything out, combine like terms. So it looks like it's going to be, and in fact, you know what? I think I'm going to go ahead and bring out a 1/2 as well. So double check me on just this algebra stuff. I got 5 minus 4r squared minus r to the 4th. But I still have this r on the outside that I forgot to distribute through. Okay, I got 1/2 on the outside that I factored out. 0 to 2 pi, 0 to 1. This becomes 5r minus 4r to the 3rd minus r to the 5th dr d theta. And then now I can go ahead and integrate with respect to r to get 5r squared over 2 minus r to the 4th minus r to the 6 over 6. And these are getting really long. And I'm evaluating this from 1 to 0. Oops, I don't know why I did this. Left my integral in. Talking and writing. So putting in 1 for r, this becomes 5/2 minus 1 minus 1/6. If we do the math on that, I believe it's going to be 4/3 d theta. And that's just 1/2 times 4/3. So that's going to be 2/3 theta. Then evaluating this from theta, going from 2 pi to 0, I get 4 pi over 3. Why don't we just do one more example in cylindrical and then we'll skip over to spherical. Example 6, we want to find the volume of the solid between these two paraboloids. Oh, I'm sorry, between the paraboloid z equal to x squared plus y squared and the cone z is equal to negative square root of x squared plus y squared plus 2. So I have a paraboloid and I have a cone. I don't know which one, how they intersect, and I need to sketch that drawing so I can get a good idea of which one is the upper function and which one is the lower function. Right? Since I'm looking at, and I'm given my z values, I just have to figure out which one is my upper limit of integration for my z values and which is my lower limit of integration. Also, I'm going to switch this to cylindrical, so I don't want x squareds and y squareds. I want r squared there. So I can see right away that I get z equal to r squared. And then on the other function, this is going to be negative. The square root of r squared squared is going to be a negative r plus 2. That would be this z value here. So I can see my z values. I just have to figure out what r and what theta is. So what I'm going to do is I'm going to look at where these two intersect. So if I set these equal to each other, that gives me, and I'm going to leave it in the r squared, so that gives me r squared equal to negative r plus 2. I already got rid of the x's and the y's. R squared plus r minus 2 is equal to 0. So this factors into a plus 2 minus 1 equal to 0. That tells me that r is equal to negative 2 or r is equal to 1. But remember, our r values that we're choosing when we're in cylindrical are positive r values, so I can ignore the negative 2. And I can just look at the r value of 1. That tells me my r values are going to go from 0 to 1. And then my theta values, well, let's look at what this is. If I look at z equal to x squared plus y squared, or z equal to r squared, that's a paraboloid opening up. So let me go ahead and sketch that. Vertex is at the origin. Now the other equation is a cone, but since it's a negative r, that's a negative a value, it's going to open downwards, but it's shifted up 2. So I'll just put that in a different color. So these intersect at these points here, and that would be projecting this down, right? That would be when r is equal to 1. Because it's projected down to the x and the y as 1. So this shadow is a circle in the xy plane, which tells me that my theta values are going to go from 0 to 2 pi. Because remember that region D, that intersection of the cone and the paraboloid, I'm looking at that shadow in the xy plane to determine my limits of integration for x and y, but I'm not in x and y, I'm in polar, so I need the r and the theta. Now we were supposed to be finding a volume. That tells me my integrand is going to be 1. If I put theta on the outside, so here's my volume, it's going to go from 0 to 2 pi. R goes from 0 to 1. And my z values, since the cone is the upper function, then that would be the negative r plus 2, but I think I'm going to write it as 2 minus r. I don't like starting with a negative. And the lower limit would be the paraboloid, so that would be the r squared. Integrand is 1. I'm going to integrate with respect to z first, but it's always an r, dr, d theta. So 0 to 2 pi, 0 to 1. Integrating with respect to z, this becomes z evaluated from 2 minus r to r squared, and then I have an r dr d theta. Alright, so if I put in 2 minus r squared, then my integrand is going to be 2 minus r squared, but I still have this r on the outside that I need to distribute through. So the volume, outer integral, inner integral, this becomes 2r minus r squared minus r to the third. And now I'm going to integrate with respect to r. So 2r squared over 2 becomes r squared minus r to the third over 3 minus r to the fourth over 4. And I don't know why I keep doing this. Copied that integral down. Okay, so I've integrated with respect to r, and notice that I'm choosing my r's to go from 0 to 1. I could have made this more complicated region, but I'm not really like I could have had r maybe from 1 to 4 or something like that, but I don't really care about that type of computation. I care more about you guys setting this up correctly. So if I put in 1, this becomes 1 minus 1/3 minus 1/4, and then minus 0. So those fractions, let's see, should be 5/12. And then our d theta, so we have 5/12 theta. And this is going to be 10 pi over 12, which will reduce to 5 pi over 6. So now we're going to move on to our spherical coordinates. So spherical coordinates use 2 angle measurements and 1 distance out from the center, whereas in cylindrical coordinates we use 1 angle measurement, and then we have some r, which is a distance from the center out in the xy plane, and then we have a z value, which is also a distance. It's a height, up or down. So we have this idea of vertical and horizontal movement in cylindrical, but in spherical we don't. We only have 1 distance out from the center, and then we have 2 angle measurements. Let's look at this first diagram, and we'll look at this point P. We have this point P. It's some point in 3-dimensional space. Well, it's going to be some distance out from the center, and that would be this first coordinate. It's a Greek symbol rho. So that would be our distance out from the center. But we also get to this point by looking at a theta value, and it's the usual theta value in the xy plane. So in this case we have some theta value around. And then we're going to look at phi. Phi is the angle measure from the positive z-axis to the point. And it's always from the positive z-axis. And since it's coming from the positive z-axis, it's going to turn out that our phi is only going to go from 0 to pi. We don't need it to be any larger than pi. Theta is going to be our usual 0 to 2 pi. We can go all the way around in the xy plane. And then rho is just some distance out from the center, so it's going to be some positive distance. So why does our phi value only have to be from 0 to pi? Well, let's look at another point. I'll draw it here. Well, notice, let me use I'll use red. So notice that to get to that point, I'm going to have some distance rho out. And then remember, our theta always starts from the positive x-axis. And if I go around, I have my theta value, my phi value. I say phi, but I think that most people say phi. Is it phi or phi? I'll say phi. The phi value is always from the positive z-axis out. So it's never going to be the case that you need phi to be larger than pi. Ooh, phi, pi. Okay, that's silly. So let's look at this next diagram. It turns out, and there's a nice proof in your textbook, that the relationship between the x and the y and the z and the r's would be that our z value turns out to be rho cosine phi, and r turns out to be rho sine phi. X is going to be rho sine phi cosine theta. Y is going to be equal to rho sine phi sine theta. Which brings us to this box below. This is how we transform between spherical and rectangular coordinates. Our rho squared is going to be x squared plus y squared plus z squared. That's actually the equation of a sphere. depending on where we are, we would use trigonometry to find our two angle measurements. Now, we can't just use tangent is equal to y over x, because remember we have two angle measurements. So that's going to be a little bit trickier. So we take that as a case-by-case basis. X, as we said before, is rho sine phi cosine theta. Y is rho sine phi sine theta. And z value is going to be rho cosine phi. In this next example 7, we're going to find our spherical coordinates, and we have our rectangular coordinates. So remember, this is x, this is y, and this is z. Well, I know that rho squared is going to be equal to x squared plus y squared plus z squared. So my rho is going to be the square root of 8, which I can write as 2 square root of 2. Okay, so now that I have rho, maybe it would be nice to use my z value. Z is equal to rho cosine phi. That seems like the simplest one to use. And I know z is 2, so I know that I have 2 is equal to, I have my rho value of 2 square root of 2 cosine of phi. Alright, so let's go ahead and divide both sides by 2 square root of 2. What we'll end up with is 1 over the square root of 2 cosine of phi, or in other words, square root 2 over 2. So cosine is square root 2 over 2 at its positive, so it's quadrant 1 or 4. So that would mean phi is equal to pi over 4 in quadrant 1. But now in quadrant 4, that's going to be 7 pi over 4. But remember, phi is only going from pi from 0 to pi. So that tells me that pi over 4. Also notice that my x, y, z, x is positive and y is positive and z is positive, so that's going to be in the first octant. If we were just looking at x and y as 1 square root of 3, that would be in the first quadrant. So that's going to be pi over 4. So remember, you're going to have choices, and it depends on your x, y, z, what octant it's in. All right, so now I have 2 of my points, right? I have my rho, and I have my phi. I just need to find my theta. So to find my theta, I can either use the x or the y. X is 1, maybe I'll just use that one. So I have 1 equal to 2 square root of 2. That's my rho. Sine of pi over 4 cosine of theta. Right. Now I'm just solving for my cosine of theta. Sine of pi over 4 is square root 2 over 2. So when I take 2 square root of 2 times square root of 2 over 2, that just gives me 2. So if I divide both sides by 2, it looks like it's going to be 1/2 is equal to cosine of theta. So again, cosine is positive in quadrant 1 and 4. Theta can be in any quadrant. So cosine is positive 1/2 when theta is pi over 3. But in quadrant 4, that would be a choice as well. But remember my original point here. My original point is in the first octant. So I wouldn't choose the theta value in quadrant 4. I would choose the theta value in quadrant 1. I have 2 square root of 2. It's always rho. And then we do phi, and then we do theta. So pi over 4, pi over 3. So a little bit of back and forth, a little bit tricky. So we'll look at some shapes that we may see in spherical, very similar to what we did in cylindrical. The first shape is a sphere. And when we look at a sphere with some radius a, then the equation is very simple. It's just rho equal to a, because remember, rho is just some distance out. You go some distance a in all directions and you've got your sphere. So a cone, you can also define a cone using spherical, and basically the same. You're just taking some phi value and you're going out some phi value, phi value from the positive z-axis, and you're stopping. And you're taking all your theta values from 0 to 2 pi and all your rho values, so that would give you your cone. You can also describe vertical and horizontal planes similar to that in cylindrical. And the equation is the same for the vertical half plane. It's just some theta value that you're going out on the xy, and then you would have your vertical half plane. Horizontal plane, which is a z equal to a, but a little bit more difficult when you're in spherical, because then it's a rho value, because it's got to be some distance out in like all directions. So it's going to be actually a secant equation. It's more complicated to do a horizontal plane in spherical. It's better to use cylindrical or just rectangular coordinates. Same with a cylinder. You can define a cylinder using spherical coordinates. It's not that nice. It's better if you just define a cylinder using cylindrical coordinates. And then another thing that might come up is a sphere with a center on the z-axis. In that case, it is shifted. Again, a little bit difficult. It's going to be 2a cosine phi. And we're only looking at phi values from 0 to pi over 2. Nothing that you would have to memorize. So let's go ahead and look at the integrals in spherical coordinates. It's a little bit fun here. So remember, in polar and in cylindrical, we had to add the r to the dr d theta. Well, spherical coordinates, you got to add a lot more than that. Now remember that our theta values before, they were constant limits of integration, some alpha to some beta, and that hasn't changed. Because they're angle measurements, they'll always be constant. They'll never be a function of another variable. So our theta, as usual, and those would be our, in this particular case, our outer, go from some alpha to some beta. And then phi is also an angle measurement, so that too will be constant, and we'll use a and b for those values. Just remember that our criteria here is that we're only using phi from 0 to pi. And our rho value is the only one that might be a function of either phi or theta. Look at the integrand. We have our function, but instead of adding an r in there, we're adding a rho squared sine phi, and then it's d rho, d phi, d theta. So as we add r with polar and cylindrical, we add in spherical rho squared sine phi. In example 8, we're asked to express this set in rectangular coordinates and identify the set. So it's just more translating. So the first thing I notice is that I have this equation, rho equal to 2 cosine phi. So on the right hand side, that almost looks like a z value, like 2z, except for it's missing a rho. And on the left hand side, I have a rho. It would be nice if it was a rho squared, because then I can replace it with x squared plus y squared plus z squared. So I'm just going to take this equation and multiply both sides by rho to get rho squared equal to 2 rho cosine of phi. And now I can replace the rho squared with x squared plus y squared plus z squared. And on the right hand side, that's just 2z. To identify the shape, I've already got everything in terms of x and y. So to identify this shape, I'm going to set it equal to 0. And it looks like I need to complete the square on the z's. So this is z squared minus 2z. And then I would simply add 1. Because I'm taking -2, half of that, and squaring it. And I'm going to add 1 to both sides. The z squared minus 2z plus 1 just becomes z minus 1 squared. So I have it in the correct form to identify this as a sphere with a center of 0, 0, 1. Is it the whole sphere? And that's where I have to be careful and go back to my phi and my theta. The theta says I'm going all the way around from 0 to 2 pi, so that's good. But phi is only going from 0 to pi over 2. So let me go ahead and do a quick sketch. The center is at 0, 0, 1. So is it the whole sphere? I don't know. I'm going to 0, 0, 1. That's my center. I'm going all the way around for my theta. But remember it's starting at the positive z-axis. My phi only goes 0 to pi over 2. And it goes on both sides. So that is actually a half sphere, the upper half of a sphere with a center 0, 0, 1 and a radius of 1. So upper half of a sphere with center at 0, 0, 1. Oops, helps if I put an R in there. And a radius of 1. Let's go ahead and evaluate a triple integral using spherical coordinates. The first thing I see is that x squared plus y squared plus z squared is simply rho squared. So rho squared to the 3/2 is just rho to the 3rd. My region D is the unit ball. Since it's the unit ball, I know that rho is going to go from 0 to 1. And it's the whole ball, so theta is going to go from 0 to 2 pi. And phi is going to go from 0 to pi. Setting up my integral, theta on the outside, 0 to 2 pi, phi 0 to pi, and I always do phi, phi, I go back and forth. This rho squared to the 3/2 is just going to be rho to the 3rd. But remember, we're switching to cylindrical, so I have to add in the rho squared sine phi. And then we do a d rho, d phi, d theta. And then just combining those rows. Oops, I forgot my 0 to 1. Forgive me for my rows. So combining the rows, I get rho to the 5th. So outer integral 0 to 2 pi, 0 to pi, rho goes from 0 to 1, rho to the 5th, sine phi, d rho, d phi, d theta. Integrating with respect to rho, notice that the sine phi, I could just ignore it. It's like a constant. So I'm just going to leave that out. And do rho to the 6 over 6 from 0 to 1. And I'll leave this sine phi out. evaluating, that just becomes, this is supposed to be a 6, sorry. That just becomes 1/6. Oops. Oh, I always forget to write things in. Sine phi. Okay, so 1/6 sine phi. Now I'm integrating with respect to phi. So sine of phi would be a negative cosine of phi. So this becomes a negative 1/6 cosine phi. And I'm evaluating this 0 to pi. And I could pull out the negative 1/6, but I can see by just putting in pi, cosine of pi is -1, so that would be a positive 1/6 minus cosine of 0 is 1. So a positive 1/6 minus a negative 1/6 would be a positive 2/6 or 1/3. So this is the integral from 0 to 2 pi of 1/3 d theta, which is 1/3 theta, and that becomes 2 pi over 3. And our last example, we want to find the volume of the solid that lies inside the cone, phi equal to pi over 3, and inside the sphere, rho equal to 2. Okay, so first of all, since I'm finding a volume, that means my integrand is 1. I'm looking at inside the cone and inside the sphere. Ooh, that's weird. Let me see what this looks like. I have to see where these guys intersect. So the sphere is easy. That's just a sphere of radius 2. So, and it's the center here is at the origin. So I have this sphere. But I also have this cone. Now the cone is, you go out 1/3. Yeah. From the Z, and you draw your cone. So where do these guys intersect? Well, they're going to intersect, and we're going to have this shape here. When I look at the shadow in the XY plane, I have this circle. That can help me find my theta. I can see that my theta is going to go all the way around from 0 to 2 pi. And I also can see that my phi is going to go from 0 to pi over 3, because that's where these guys intersect, right? Where my phi is a distance of pi over 3. Let me think about what my rho is going to be. So, got my theta. I have phi. Now let's think about this rho value. If you take any point here, the distance out in the rho value, remember it's from the center out, is always going to be a maximum of 2. So my rho goes from 0 to 2. So now that I have my limits of integration and I know my integrand is 1, I can simply find the volume. 0 to 2 pi, 0 to pi over 3, 0 to 2. Remember, it's a rho squared sine phi. And then you do d rho, d phi, d theta. Integrating with respect to rho, I'm going to have rho to the 3rd over 3. And I'm going to pull the sine of phi out. I really don't need that since it's like a constant. And then this was from 0 to 2. So it looks like it's going to be 8/3 minus 0, or 8/3 sine phi. Now integrating with respect to phi, sine of phi becomes negative cosine. So this is going to be negative 8/3 cosine phi. And again, you can pull out the negative 8/3. I'm just going to leave it in because these computations are not bad. Maybe I should have taken it out because this is a pi over 3. Cosine of pi over 3 is going to be ugly. Well, I guess it's not that ugly because cosine of pi over 3 is 1/2. So that looks like it's negative 4/3 minus cosine of 0 is 1 minus a negative 8/3. So it's negative 4/3 plus 8/3, which would give me a positive 4/3, I think. And then integrating with respect to theta, I have 8 pi over 3 for my final answer. Alright, so that's it for this section. Kind of a long section. I wanted to do more examples, but that unfortunately would make this video even longer and longer to upload. So that's it for this section.